Okay. I hope tomorrow I can go to the class. Okay, we are now in rotational dynamics. Yes. Yesterday we discussed the torque, which is the first quantity in rotational dynamics, which is the force. This is yesterday's lecture. The torque is the rotational effect of any force, which is depends on the radius or the position where that force acts on any rotating object. Also the direction of that force with respect to that radius, which is theta. And we can find the torque as R multiplied by the force F multiplied by sine theta. This is the perpendicular distance. Perpendicular distance means we need the normal force or the perpendicular force to the radius. Okay. And we can add torques together just as we did for the force, yes. And we solve an example and we found the total torque, which means we found the total force or rotational force, and it has a direction, and its units is newtons, but multiplied by meter, as you see here. And the torque has a direction, which is the direction of the rotation or the direction of the axis of rotation. Okay. Any question about torque from yesterday? Because we will go on today and study things just like what we did for the linear force. As you see here, now we will deal with Newton's second law. This is the lecture today. It is maybe 13 pages. Do you remember Newton's second law, which is F is equal to ma? We just need to multiply it by R, the both sides of the equation. It will be RF and R, this is R, multiplied by A. But A from the first week, the first day or the second A is equal to R alpha. Alpha is the angular acceleration. And we know that the velocity is equal to R omega. We will see that many times. This is the connection between the linear motion and the angular motion. So A, the acceleration, is equal to alpha R. And we multiplied by R, so we have two R's in the right-hand side. And we have one R in the left-hand side. R multiplied by F, it is the torque. We just talk about it. We have R alpha R. So R with R, it is R squared. We have R squared multiplied by alpha. R squared, if you remember in the previous lecture or the lecture before, it is the moment of inertia, which is I, moment of inertia. We are talking about point mass, but if we have any extended object, then we will put this factor here, which is 2/5, 1/3, 1/12. That depends on our object. But it is in general the moment of inertia, which is R. Now the torque is equal to I multiplied by alpha. Remember that F, the same as the torque. F is the force in linear motion. The torque is the force in angular motion. The mass is the ordinary mass in the linear motion. I is the rotational mass or the rotational effect of the mass. A is the linear acceleration. Alpha is the angular acceleration? It is the same. It is just Newton's second law, but in rotational form. Okay? It is just mass multiplied by acceleration in rotational motion. Any question about this? Just if you remember this one, you have to remember this one. It's simple. Okay? Now, we have an example. Okay. We have this system. It is a cylinder, solid cylinder, with radius R. It has a mass M, capital M. Its length is 0.5 meter. It is rotating, and this is the axis of rotation, which is the direction of the rotation, and it is a direction of the torque. There is a force acting on this cylinder. There is a rope here, and this rope is rotating with the cylinder, and its end hanged with the mass M, and there's a weight downward. It is a force due gravity, which is a weight. It is the capital W, not omega. Okay. If the mass is 10 kilograms, then the force in this case is the weight, which is 10 multiplied by G, 9.8. So the weight or the force is equal to 98 newtons. So now here in this direction, we have a linear force, 98 newtons. If the properties or the quantities for the cylinder are given here, the mass of the cylinder, which is capital M, it is 30 kilograms. The radius is 0.1 meter. The length is 0.5 meter. The mass, hanged mass, is 10 kilograms, and we found the force due this mass, which is because the weight of its weight. Now simply, if we need to find things, what we can find? Yes, the torque acting on the cylinder. The torque, it's coming from this force, which is 98, as we see here. And if we have a force acting like this, if we multiply the force by the radius, which are perpendicular here, it will give us the torque. So the torque is equal to, as we see, R multiplied by F is the torque. What is the torque? It is R multiplied by F by sine theta. As you see here, this is R, this is F, which is the weight. R 0.1, the force is 98, and sine theta, sine 90 is 1. So the torque is equal to 9.8 Newton meter. It is a force, but a rotational force. So we have another unit, which is the meter. What is the angular acceleration? We need to use the Newton's second law, this one, in rotational form. Tau is equal to I multiplied by alpha. Okay. As you see, tau is equal to I multiplied by alpha. We need to find alpha. Tau is known. I, we can find it. I is the moment of inertia for the cylinder, which is half, as you see, half mr squared. It is from the table shown in the, which is shown in the book and shown in the notes of our lecture. So M is given, it is 30 kilograms. R is given, it is 0.1. So I can be found, it is here. So alpha, if we divide the both sides on I, it will be tau over I equal to alpha. Okay, we can find alpha. Tau, 9.8. I is half, the mass 30, 0.1 square, which is the radius. So the acceleration is 65.3 radians per squared second. It is acceleration, but it is not meter per square second, it is radian because it is angular. Angles acceleration. Okay. Any question about this? Now I will move to there's no chat. Now I'll move to work and power. You remember that we talk about work in linear motion, which is F multiplied by X. The work is F multiplied by X by cosine theta. Assume that cosine theta is equal to 1 if theta is equal to 0. The force, because the force in the same direction with the change in position. So theta is 0, cosine theta is 1. So this is the linear work. We know it from before. Okay. X, it is for a rotational motion. This is the displacement. Oh no, it is not a displacement. It is a distance because it is not a direction. But if it is limited and short, it can be a vector. From before, from the connection between the angular motion and the linear motion, this section from the circle is equal to the radius multiplied by the theta in radians. So X is equal to R delta theta. Just put it in X place. So the work is equal to F R delta theta. But we know that FR again, it is the torque. So it is the torque multiplied by delta theta. As you know from before, the work is equal to the force multiplied by the distance in linear motion. Here we have the work, it is the force in rotational motion multiplied by the distance in rotational motion, which is theta. So the equations are the same. Because you understand the work from before, we can understand the work now, but we just need to change the force to its rotational form and the displacement to its rotational form. It is tau, which is torque multiplied by delta theta. Okay. Delta theta is theta 2 minus theta 1. I need to achieve another thing now, which is the kinetic energy. We talk about the kinetic energy in angular motion. It was 1/2 I. It is here. It is another way to derive the kinetic energy in rotational motion. The torque, as you know, is the moment of inertia multiplied by the acceleration, which is Newton's second law, and this is delta theta, which is theta 2 minus theta 1. I is I. Alpha, the angular acceleration, it is the change in omega with respect to time. Okay, multiplied by delta theta. If you just take the time for theta, it will be omega, delta theta over delta t, like this. It is omega. So we have I, which is the moment of inertia or the rotational effect of the mass, multiplied by omega. This is omega, multiplied by delta omega. So we have this relation. This is the work. For small periods, delta will go to D. And we have the relation, the work is equal to I omega dW. And if we do the integration, and this is not required from you, in the next page you will see that this integration is not required, but I just need to show you that we have the work after the integration. We have the terms 1/2 I omega squared 2 minus 1/2 I omega 1 squared. You can see this is the kinetic energy. We deal with this term from before. We know the kinetic energy in rotational motion because I refers to the mass, omega refers to the velocity. This is another way to derive the kinetic energy and its relation with the work. This thing is not required from you, but just to show you. Okay, now the work is equal to the change in kinetic energy. Again, just like what we see in the previous week. It is the work energy theory. The work is equal to the change in kinetic energy. We did that. You solve questions in the exam about this. Look, this is the previous week relation. The work is equal to the change in kinetic energy, 1/2 mv squared. What is the power? We have another thing, which is the power. The power now, it is the work or the change in work or the work go through the system derived over the time period. The work, it is the torque multiplied by the angular distance or displacement, which is theta. This is the work, T, tau, delta theta. We found it here. Where is the work? Yes, this is the work. Tau, delta theta, it is the force multiplied by the angular displacement over delta T. Now delta theta over delta T, it is omega. It is the velocity. Just like x over t is equal to the velocity. This is the angular velocity. So the power again is equal to the time of the energy flow or equal to the velocity of the force. This is just what we did in the previous week. The power is delta W over delta T, which is the power which is equal to the velocity of the force. I said from before, the power is the velocity of the force or the time of the work. It is the same here. This is the velocity, the angular velocity of the angular force. We just a new term, which is angular in our physics now. Now we have this example. Any question about this? Okay, no questions. For this game, if we have, you know, there's in the, again, I don't know what is the name of this. We have an engine. This engine is rotating this big disc, and there is a mass hanged with that disc. If the radius of this disc is 6 meters, it is big. And the cart mass is 1,000 kilograms with the people inside it, okay? This mass. The angular velocity, which is constant because we have an engine here, so it rotates it with constant velocity, and it is 2 pi over 60 radian per second. 2 pi means an angle, 2 pi, which is 360 degrees, or one rotation, right? 2 pi, it is one rotation during 60 seconds. So it is rotating one rotation during a minute. Okay, what we need to find? It is okay, it is given the velocity. It is 2 multiplied by 3.14 over 60. We can find it as just a number. Now we need to find the torque effect by the engine. Okay. Also, we need to find many things. We need to find the work done to lift the cart from the bottom to the top, I think. Yes. We need to find the work to lift this mass from here to here. From here to here is 6 meters, the radius. But from here to the top, it's 12 meters, okay? The engine's power. We have the velocity. We will find the torque. The velocity of the torque is equal to the power, simply, the angular velocity. The rotational kinetic energy, also we can find it. Let us look and see the torque. Now, from the work, the work is equal to, we need to find the torque now, okay? The work is equal to tau multiplied by delta theta. Tau is tau, which is the torque. Delta theta, I take it equal to pi. What I mean by pi, which is the motion from the bottom to the top, pi. From here to here, it is 100, and from here to here. From the bottom to the top, it is 180 degrees, which is a pi. Okay. What we can do from this, let us see. We cannot find the torque yet because we don't know the work, because the work is the second requirement. So the first requirement, we cannot find it until we find the torque, with the work. Let us go to the work. The work is equal to the change in potential energy. At this point, the potential energy is mgh. H at this point is 0. Okay. H at this point is equal to 12. So the change from here to here, it is a potential energy, and we need to do a work to give our mass that potential energy. So the work should be equal to mgh. Yes, there is a negative sign here, but there's a negative sign for G also. So we have a negative sign for G and a negative sign for U. You remember that the work is equal to the positive change in kinetic energy, but it is equal to the negative change in potential energy, but we have a negative sign in G here. So it will be finally, it will be positive. The mass is 1,000 kilogram, G is 9.8, H is 12 meters. So the work needed to lift the mass from the bottom to the top is easier to compute from the torque. So we compute it at first. It is 117,600. This is 117,600 joules. Okay. Now we can use it to find tau. Theta is given pi. The work is found now. We can find the torque. Now to find the torque, the work is equal to the torque multiplied by pi, which is this value, we found it. So the torque divide over pi the both sides, the torque is equal to 37,400, and this value Newton per meter. Not per, multiplied by meter, I'm sorry. Pi is 3.14. You need to put. So yes, I give you the torque to find it initially, but you cannot find it until you find the second requirement. This is physics, okay? But you do a step, then you do the other step. Okay, but the relations are simple. Now, the engine's power. Okay, we have the velocity. The velocity, I told it is 2 pi, one rotation over 60 seconds. The torque is found now. So multiply the torque by the angular velocity, it will be 3,920 watts. Another way to find the power, which is the power multiplied, divided over the time period. The work is found, which is 100,000 and something, over the time to move the mass from the bottom to the top. For a full rotation, we need 60 seconds. For half, this is half rotation, we need 30 seconds. We don't need 60 seconds. So the work, if we divide it over for half rotation, over half the total second, the total period, the total period is 60. Half of it is 30. If you divide this over its period, its time, It's the same power as you see here. As you see from the angular velocity, we need 60 seconds for a full rotation, but we don't have 2 pi, we have 1 pi, just 1 pi. It is 30 seconds. What is the kinetic energy? We can find the kinetic energy by 2 ways. By putting the value of the kinetic energy, which is 1/2 I. This is the kinetic energy for the mass. For the mass, not for all the system. It is not for the disk, for the wheel. It is just for the mass. It is, and we can assume it as a point mass in this case. Okay, assume the cabinet as a point mass. It is 1/2 the moment of inertia multiplied by its velocity. The moment of inertia for a point mass is mr squared. The velocity is given 2 pi over 60 squared. So the kinetic energy is 197.4 joules. Okay. And we can find it by using the work. It is equal to the change in kinetic energy if we assume the initial kinetic energy is equal to 0. This is an example, contains everything that the torque, the work, the energy, and so on. Any question about that? Okay. Let us move to another thing. Now we use the Newton's second law. We used also the equations of motion. Also, we used the kinetic energy and the potential energy, and we found the power. We still need to look at the momentum, which is the angular momentum. The linear momentum was P. Now the angular momentum is L. Okay. Again, from the linear momentum, we can reach the angular momentum. By the definition, just multiply the both sides by R. If you multiplied R multiplied by P, it will be the L, which is the angular momentum. If we multiplied R by the linear quantity, it will give us the angular quantity, just as we did here when we found the work. Yes, the force, the torque. Where's the torque? It is here. When we multiplied R by the force, it gives us the angular force. If we multiplied R by the momentum, it will give us the angular momentum, just like this. We have R from the left hand and R for the right hand, which is here. If we multiplied R by the velocity, it will be not the angular velocity, because this velocity is equal to R omega, if you remember that. It is R omega. So it is here. You can see it here. So the angular momentum is equal to mRV. mRV is equal to angular momentum. This is mR, and V is equal to R omega. So it is mR square multiplied by the angular velocity. mR square, again, it is the moment of inertia, which is the rotational effect of the mass. Again, the momentum is equal to the mass multiplied by the velocity, but in angular motion, which is the angular velocity, angular momentum in this case. And its unit now, it is not kilogram meter per second, it is kilogram meter squared per radian per second multiplied. Okay, this is the unit. So now we have angular momentum. Okay, there is a connection between the momentum and the force. We saw that from before also. The change in momentum with respect to time, it was the force, delta P over delta T. It was the average force. And the instantaneous force was dP by dt, which is the small changes. But any change in momentum with respect to time will give us the force. This is in linear motion. What about the torque? Okay, let us look at it. The torque is equal to I omega. Any change with respect to time of the torque, we can apply it here. I is the mass, it is constant. We can take it out from this change. It is here out. So delta omega over delta t, the change in velocity with respect to time, it is the acceleration. It is alpha, it is the angular acceleration. I, it is the angular mass. Alpha is the angular acceleration. It is just Newton's second law of rotational motion. We just found it in the first of this lecture. So any change in angular momentum with respect to time will give us the torque. It is just as the linear motion. Any change in linear momentum with respect to time will give us the force. This is Newton's second law in general form, as we said before. Now, we are dealing with the vectors, okay? If we have a rotating object about this axis, we don't know what is the direction of this axis. Is it X, Y, Z? We don't care, but it is axis of rotation. Omega, starting by omega. Omega, it is the angular velocity about this axis because we're acting by a force. The direction of omega is the direction of that axis. So this is omega direction. Because the momentum, angular momentum, is equal to I multiplied by omega. It is a vector. Omega is a vector. So the angular momentum has the same direction as omega because I doesn't have any direction. So the direction of angular momentum is the same as the direction of omega. So angular momentum is parallel to omega. We will see that. The torque is the change in angular momentum with respect to time. The time has no direction, so the torque has the same direction of the angular momentum. The angular acceleration has the same direction of the torque. So all of these quantities have the same direction. So the direction of the angular momentum is parallel, which is the same, the direction of the torque, which is the same or parallel to the direction of omega, which is the angular velocity, and which is the same to the direction of the acceleration. All of them have the same direction, which is the axis of rotation. Okay, the rotation counterclockwise is positive, clockwise is negative, okay? Now we have this long example. We are on page 7, and this example has 4 pages to solve it, okay? But I think it contains everything. Also, by doing this example, we finish our lecture today. We have this roulette wheel, okay? We need to assume it as a disc, just to simplify our calculations. It is radius R 60 centimeters or 0.6 meter, okay, from its center to its edge. And its mass is 2 kilograms. All of the mass is 2 kilograms. We have the big R is 0.2. The big mass is 2 kilograms. It is rotating initially it is rotating by velocity, which is 2 pi over 1 second. 2 pi is meaning 1 rotation, as we see in the previous example. So we have 10 rotations per second. It is fast, as you see. So this is initial, or omega 1, you can assume it, or omega initially. Now we are talking about a conservation of angular momentum. We have a collision. This collision, previously we dealt with the collisions in linear motion, the elastic and inelastic collisions in linear motion. Now we will deal with elastic and inelastic collisions, but in rotational motion. It is the same equations, but in rotational form. If we have a ball, its mass is 0.1 kilogram, settled in a cell at a distance 0.5. So the radius is 60, and the ball jump to this disk, and its place now is r equal to ½ meter from the disk center. Now we have another force. We have another mass. Do you expect that the velocity will go down or stay the same, or go speeding more than the initial velocity? All of us, we know that if we have a disk and we jump to that disk, its velocity will go down. It will change its velocity to another slower velocity. We will see that now. We need to compute many things. Compute the initial angular momentum for the disk without the mass. Find the angular momentum after the ball be at the radius. Okay. Find the final angular momentum, angular velocity, the torque affected by the ball on the disk. Wow, it is. And the force from the disk on the ball. If the collision time is 0.1 1/second. Now, if the ball come here and it's settled during 0.0 second, we can find the force or the torque done by the ball on the disk, and also from the disk on the ball, which is equal to the equal to the same force, but with negative direction. Okay, the change in rotational kinetic energy, the kinetic energy initially, the kinetic energy finally, the work done by the disk on the ball, and we can find many things. Let us start these calculations. It is just a long example, which is which contains everything. Okay. Now we have the disk, we have the ball. The angular momentum for the disk, it is I for the disk multiplied by its velocity. We have the angular momentum for the ball, which is its moment of inertia multiplied by its velocity. I'm talking initially, which is 1 here, initially. For the disk, the moment of inertia, it is ½ mr² from the table. Its omega is given 10 to pi over 1 second. In z direction, all the rotation is in z direction, as you see. Okay. L for the disk is 1/2, the mass 2 kilograms, the radius is 0.6 squared, multiplied by the angular velocity, it is 22.262 by its units, kilogram meter square, radian per second. What about the ball? Before it's jumped to the disk, its moment of inertia, it's a point mass, mr², but its angular velocity, it was 0. It is not rotating down. Initially, before our experiment, it has 0 angular momentum. So the total angular momentum for the system is L for the disk plus L for the ball, which are this plus 0, which is this value. What is the final angular momentum? The angular momentum should be conserved. Okay? So the final angular momentum should be equal to 22.62. So L2 should equal to L1, which is the angular momentum of the disk plus the angular momentum of the ball, which is 22.62 with its units. Okay, again later. What is the angular momentum after the collision? It is the angular momentum of the disk plus the angular momentum of the ball. But now the ball has angular momentum. It has a velocity, which is the same angular velocity of the disk, which is omega 2. It is just now the two masses have the same velocity. So it is like the inelastic collision and the sticky collision, right? And we have two masses or two angular masses, which are the moment of inertia for the disk and the moment of inertia for the ball. We can find now omega 2, which is the angular velocity after the collision. So the total angular momentum, it is constant, which is equal to the total moment of inertia multiplied by the angular velocity, divide over the mass, the moment of inertia, the both sides. It will be like this, 22.62 over the moment of inertia of the disk, over the moment of inertia of the ball here, then the angular velocity will be 58.675. Remember that the angular velocity initially, it is 10 rotations, which is 2 pi over per second. It was, if you find this value, it was 62.83. So this is the initial angular velocity. This is the final angular velocity. This angular velocity, it is 9.35 rotations. But initially it was 10 rotations. So the velocity now is slower, as you see here, because we have a new mass rotating with our system. Now, we can find the angular momentum for the disk, the angular momentum for the ball after the collision. We need just to use the final velocity, which is 58.75, multiplied by the moment of inertia for each one of them. The moment of inertia for the disk is this. The moment of inertia of the ball is this. So the angular momentum for the disk is 21.15. The angular momentum of the ball is 1.47. Add them together, they will give us the total value of angular momentum, 22.62. Okay, the torque now. As you know from the Newton's second law, we just talk about it, any change in momentum with respect to time will give us the torque. Now, the torque from the ball on the disk, it is the change affected on the disk momentum with respect. So the ball affected on the disk, it will affect on its momentum, the change in its momentum over this time period, which is 0.01 seconds. So it is the momentum finally minus the angular momentum initially. The momentum finally, it is 21.15. This is 21.15, which is L finally. The initial momentum is 22, which is the total momentum. So now the torque from the ball on the disk, it is negative 147 Newton meters in the Z direction, negative Z direction, because the ball will act. Imagine that the ball come here and the disk is rotating counterclockwise. The ball will affect clockwise of its collision. Assume yourself jumping to the rotating disk, your effect will be to the opposite direction of that rotation. So the torque done by the ball, it is in the opposite direction, which is the negative sign in Z direction. And the torque done by the disk on the ball, by the same way, it is the change in momentum of that ball divided on the time period, which is 1 per second, it will be positive 147. It is the same value. It is in Newton's third law now. The same magnitude, opposite direction. Okay? Newton's third law, as you see here in this note. Okay, the change in kinetic energy. For the disk, we can find it. We have the moment of inertia for the disk is the same, which is half mr squared. We found it. It is 36%. Omega final squared minus omega 1 squared. We just take all of this as a factor, common factor. Omega, finally, we found it after the collision. This is omega initially before the collision. So the change in kinetic energy for the disk, it is negative change in kinetic energy, which is negative 89 per 0.3 joules. Yes, because its velocity gets slower because of the ball. It takes part of its energy. What about the change in energy for the ball, which is the kinetic energy for this ball? If you compute the initial kinetic energy for the ball was 0 because its velocity initially was 0. And its velocity finally is the same as the velocity of the disk finally, which is 58.75 squared. And the gained energy by the ball is 43.14. So the lost energy by the disk is, 89 joules. The gained energy is by the ball is 43. It is almost the half of the energy. So we have another part of the energy, and this part of the energy is lost in this experiment. Because of that, this collision doesn't conserve the kinetic energy. It is not conserved like the momentum. So it is inelastic collision. What about the work? The work is the change in kinetic energy. There is a work done on the ball. There is a work done from the ball on the disk, and they are the change in kinetic energy for each of them, which is 43 joules and 89 joules also. Now, let us see this notes finally. Note that the angular momentum is conserved. Yes, which is a collision and rotational nature system. Yes, it is a collision and rotational system. The two objects became one object after the collision. This makes the collision inelastic because we change the form of the collision, of the system. We change the shape of it. It is inelastic collision, and the kinetic energy will not be conserved in this collision. Note this thing, I don't know what is the word here. Note also the dancer. Yes, the dancer. And the total moment of, yes, if you look at the dancer here or rotating object, You know the dancer on the ice. If the dancer open his or her hands like this, its velocity is slow. But when he or her close his hand, then the velocity will become more and more. This is because the angular momentum will stay conserved and the velocity will increase by this motion, by changing the moment of inertia. In this case, we change the moment of inertia. And that's it for today. Any question about today's lecture? Please look, today I will put another homework, maybe tomorrow, but you have a homework here, which is homework about not here, yes, here. It is a rotational kinematics. And I will prepare a quiz. And for this new quiz, you have just one attempt to do it. It will be open book or open notes quiz, but you have one time to do it. And I think that's all for today. If you don't have any question, thank you for today's lecture. Okay.